Hello all, welcome to the I think last session of the beam design. Okay, we have seen overall what are limit state method. From there, if I say then beam, in the beam, if you remember, we know how to put the reinforcement at the bottom, at the top, like AST, ASC, and in the previous session, last two sessions, we have seen how to put a shear reinforcement also, how much spacing to be provided, or what are the stirrups, all those stories, incline stirrups, bend up bars, everything. So we know all those things. Now final touch up is, there are two cases. If there is a torsion acting in the beam, how to include the torsion. Okay, first case, that's what we are going to in this session. I will try to include the next session of bond and development, and if we have time, so we will include that bond and development also in this session. Okay, we'll see how it goes. So we are going to see some theory and some few problems in this torsion. Okay, so if the line of action is not passing through your shear center, okay, I hope you know what is shear center. If you are applying the load, there won't be any twisting in the beam. If there is like a center of gravity, like a centroid, there is something called shear center. If most of you doesn't know, please go through like online something like that for see what is the shear center. Every cross section will have some shear center point. C section, T section, rectangle section, everything will have shear center. If I am applying a load over the shear center, it will not create any twisting in the beam, in the section. Okay, twisting means, I hope you it is clear, like a twisting a chalk piece. This is a different type of load coming to the beam, right? So there are two types of twisting can happen in a beam. One is primary torsion, second one is secondary torsion. Primary torsion is officially the twisting will happen to the beam. It is like a circular beam in the water tank. There is a 100% chance of twisting. So we have to design compulsory for the torsion in that case, and curved beams. Okay, in a plan, if you look, it will be looking like a curved beams. Secondary torsion, you no need to design for a torsion. You may or may not expect the torsion will happen. Okay, so it's something like a bending of two beams are connected. One beam is bending, that is creating, considered like a long T beam. Okay, not like a one beam is going in like you consider X and Y in the paper. One beam is in X direction, one beam is in Y direction. Consider this X is bending. Okay, when X is bending, this beam in Y will try to get twisted. Okay, so there is a small twisting will happen in the another beam, right? So something like that. So you have to include that torsion, extra torsion, or how to include that extra torsion in the design. Okay, we know so far how to do, what is bending moment, how to design for the bending moment, and what is shear force, how to design for a shear force. So using the two factors, we will try to include the torsion in that shear and bending moment. Okay, because moment and moment are same, right? You see the T equal to P into E, force into E is a eccentric distance. Okay, force into distance is nothing but a moment, right? So torsion can also be considered as a moment, but the torsion is acting in some other axis. That's it. Okay, if moment is acting in longitudinal axis, torsion is acting in some other axis. Okay, so I hope it is clear what is torsion and how to design for a torsion. So we are dividing the torsional topic into two things. One is for torsional shear. We will include the torsion, shear created by the torsion. Consider again the chalk piece example. In the chalk piece, I am applying a torsion at the ends. The chalk piece breaks and the failure is shear. Correct. So when I am applying a torsion, there is a shear force being generated. Okay. So I am dividing the torsion into two cases. Something I will apply a changes to the usual shear force you had, and I will apply some changes to the usual bending moment you had. So if you see, this is the formula to include the torsion in your problem. VE, that equivalent shear force, is equal to usual shear force you are having. That VU, I hope you remember what is VU. VU is nothing but the shear force coming from outside because of the load, because of the SFD. If you draw SFD diagram, the shear force coming is nothing but VU. VT is the shear force because of the torsion. What is the formula? 1.6 TU by B. That is the extra shear force we are including. Now using this VE, we will use to do all the procedures like how we solve the previous problems in shear force. Okay, we will use, instead of VU, if you go back to the shear, so what you did everywhere, you see this such problems, in step 1 you used VU, right? And similarly here in this case we will use VE. That's it, not a big change. Instead of VU, we will use VE because we are adding some extra shear force because of the torsion, that is 1.6 TU by B. Okay, so tau VE equal to VE by same procedure. If this shear stress generated is lesser than 0.5 tau C, greater than 0.5 tau C, everything is same, nothing else changed. Only instead of VU, where we are using for a shear formula, we will use VE. So V is nothing but Vu plus Vt. Vt is nothing but 1.6 Tu by B. Nothing else changed. Only that extra first term changed. Remaining everything is same procedure what you used to design the shear. Okay. So next, design for torsional moment. What will you do here? If your tau VE is nothing but this step 2 tau VE by BD, nominal shear stress. Okay, the shear stress coming from outside. If tau VE is lesser than or equal to tau C, then no need to change anything in the bending moment. It is bending moment is nothing but mu. Okay, if tau VE is greater than tau C, means externally coming nominal shear stress is more than the tau C value, then you have to change the bending moment because there is, the torsion is creating some extra shear force. So this torsion has to be considered. So how will you change the bending moment? Usually you know what is mu. Mu so far you know, right? 0.33 FCK B into D minus 0.42 into X something, that one. Here in this case, Tu into 1 plus D by B divided by 1.7. This is the extra bending moment, torsional moment created. This you will get, this you will add along with the moment. This Me1 you will use to calculate the AST. I hope you remember the formula for calculating AST is 0.87 Fy AST D minus 0.42 into XU. Correct? Mu equal to 0.87 Fy AST D minus 0.42 into XU. Now instead of Mu you will use Me1. So what is Mu1? Mu plus some torsional moment. What is torsional moment? Tu 1 plus this formula you have to memorize. Okay. So for compression steel, I hope you remember you used Mu minus Mu limit to calculate the ASC value. Okay. If you are very clear with the previous lectures, you will know to calculate the ASC value, area of compression in steel, you use the formula Mu minus Mu limit. In this case, for calculating that one, Me2 will be this Mu2, extra bending moment will be nothing but Mt minus Mu. Okay, Mt minus Mu will give you the extra bending moment. That moment you will use to calculate the ASC value. Okay, and also remember ASC is required only if Mt is greater than Mu, or else you don't need to design. Mt is nothing but the torsional moment. Torsional moment that Tu into that formula. The torsional moment, if it is greater than the ultimate moment, then you have to design the ASC also to tackle that twisting. Okay, if Mt is lesser than Mu, then no need to provide this one at all. Okay. So we will solve one or two problems. It's GATE 2008 question. An RCC beam of rectangular cross section of width 230, effective depth 400 mm is subject to a maximum factored shear force of 120 kN. And same question. I think we have solved some question. The FCK, Fy value, steel value, everything is given. For the area of main steel provided, the design shear and tau C is given. The beam is designed for collapse limit state. In addition, you can pause and write the question if you want, or you can write the given. In addition, they have told the same beam is subject to a torque whose factored value is creating some, it is given in 10.9 kilonewton meter. The stirrups has to be provided to carry a shear equal to what? So the stirrups has to be provided to tackle what type of shear force they are asking. Okay, so this extra shear force, it's very simple. The beam is being subjected to torque Tu, right? So 10.9 kilonewton meter is given. Ve you know, Vu plus Vt, actual shear force plus extra shear force 1.6 Tu by B. Actual shear force, factored shear force they have given 120 plus 1.6 into 10.9 divided by width is given 0.23. Substitute everything, you will get the equivalent shear force of 195.83 kilonewton. But they are, remember the question, they didn't ask you the equivalent shear force. They are asking for what shear force the stirrup should be designed. That should be extra shear force, right? So VE minus tau CBD you should put that 195 minus this tau C is 0.48 is given, B into D you substitute, you will get answer 151 kilonewton. So the extra shear force to be designed is 151 kilonewton. Okay. So next question. At the limit state of collapse, an RCC beam is subject to a total flexural moment of 200 kilonewton meter. Shear force is given, torque is given. The beam is 300, beam dimensions are given, 300 mm wide, 425 mm depth. Effective cover is given. The equivalent nominal shear stress. So this get 2004 question. Equivalent nominal shear stress calculated using the code turns out to be lesser than the tau C. They have given clearly the tau C. Okay. Equivalent nominal shear stress is nothing but tau VE is lesser than tau C. They have given. So what is the equivalent shear force? They are asking VE, I think VE, and then they are asking Mu1 for designing the longitudinal tensile steel. Mu1 is they are asking. Okay. So beam is subject to torque. They have given, you just write the given Tu9, Vu20, Mu200. They have given. So VE equal to Vu plus Vt. That's what they asked as the first question. Vu plus 1.6 Tu by B, 20 plus 1.6 into 9 by 3. This will give you 68 kilonewton. So Also they have given nominal shear stress is lesser than tau c. That means no need of bending moment, right? No need of if you remember the condition 1 what I told you, if nominal shear stress nominal average shear stress is lesser than tau c, then the bending moment to be taken as the same bending moment, you no need to change anything for torsion. So this is the twist in the question. So mu1 you should take that directly, mu what is given 200, you should not use that formula and multiply. Remember they have given tau v is lesser than tau c, so the given bending moment to be taken as the actual bending moment for designing the AST. Okay. So next question, an RCC beam of size 300 into 1000 mm deep beam, okay, 1 meter depth, it is subject to a shear force of 150 kilonewton, bending moment 150 and torsion 30 kilonewton meter at a limiting conditions, everything is at extreme condition. What is the equivalent bending moment and equivalent shear force at ultimate loads? Okay, they are asking. So the beam is subject to torque, they given B depth over everything is given, VU 150 kilonewton, MU 150 kilonewton meter, TU 30 kilonewton. So VU plus VT, you just substitute everything in the formula, you will know equivalent shear force is 310 kilonewton and the equivalent bending moment, you just substitute everything, D is given 1 meter, this is, you substitute everything, you will get answer 226.47 kilonewton meter. It's a very simple straightforward question. So one more question, okay. So an RCC beam of size 300 into 600 mm is subject to a factored value of shear force 100, bending moment 100 and twisting moment 34. So they are asking for a longitudinal tension, so they are asking mu1, okay. That is a question number 32, and question number 33, they have changed the moment from 34 to 68. They are asking what is the moment to be designed for ME2, they are asking for the compression steel, okay. So answer, so write the given, B is given, D is given, VU, MU, TU is given, they are asking MU1, right, directly substitute the formula, MU equal to TU, substitute everything, 68, 1 plus 0.6 by 0.3 everything, it will give you 120 kilonewton meter, and remember MT is greater than MU, correct, because MU1 you got 120, give me a, okay. So for clarity I have edited the slide again, so I will give you a clear perspective of this problem. The given B is 0.3 meter, D is 0.6 meter, VU is 100, MU is 100. For the first question in 32, TU is 34 kilonewton meter. So the equivalent bending moment is MU plus TU, all those things, you substitute everything, TU is 34, you will get 160 kilonewton meter as a first question answer. Second question, they have upgraded from 34 to 68. And they are asking how much extra moment to be designed for the compression steel. You can go back and see the previous question. So I am calculating only MT, TU into 1 plus D by B by 1.7. If I do that, I am getting approximately torsional moment is 120 kilonewton meter, which is higher than MU, right? MU is 100. So we need a compression steel. This, the first condition is satisfied. And how much moment ASC should be designed is nothing but MT minus MU. So 120 minus 100 is 20 kilonewton meter. This will be your answer for the second question, and for this moment you have to design the ASC, area of the compression steel, okay. So with this we have discussed the objective oriented problems for the torsion, for calculating equivalent shear force and equivalent bending moment for tension steel and also for a compression steel. So I will go to a small chapter we have left is design for bond and development length, and we have some theory and few problems here, okay. So what is bond stress? It is a I hope you know, it is a shear stress developed between the steel bar. You can see the figure, there is a steel bar inserted inside the concrete, and there are two types of the bond, you need a bond throughout the bars, right, throughout the bars along the beam, but also at the end. So I will come to that. There is an anchorage bond and flexural bond. In this case the bond is nothing but a shear stress which is going to develop between the steel bar and the surrounding concrete, okay. I hope with your common sense you can realize that instead of mild steel bar where there will be a smooth bar or smooth surface, and for a Fe415 or Fe500 you have a tar steel, so we have more friction, so there will be a more shear stress you will get, okay. So you see this types of bars here. If you are using the value of bond stress is a function of FCK value, okay, and it is a function of types of reinforcement I just told you, and type of force, whether it is you are applying a tension or compression, how much force you are applying here, okay. So if you are using a plain MS steel bar, and if your bar is under tension, you can directly use the tau BD for, you can see what I have discussed here, factor F is, you can see the bond stress formula, F into tau BD. Tau BD is a bond stress which mostly they will give you in a problem, we give you in a formula, okay, in a question. So you have to just multiply that F value. If if the given question is having plain mild steel bar in tension, then you have to use directly the tau BD. If they are giving plain mild steel bar in compression, you have to multiply 1.25, 25% more bond you will get. If you are using, why you are getting more in compression. If you know the Poisson effect, when you are pulling the steel bar outside, the central width will come down, central depth will come down. Okay, when you are pulling the steel bar in anything, if you take a boom or bubble gum or something, if you are pushing the central thickness will come down. When you are compressing it, the thickness will go high. So when the thickness is going high, so whenever there is a compression in the steel bar, the thickness will increase, the diameter of the bar will increase, then you will have a more bond. So the compression will have more values. Okay, so the plain MS, you can note the table here. If you are using HOST bars, you will have more bond, and if it is in tension 1.6, HOST bars in compression you will have 2. Okay, so next topic you should know is the development length. From this figure you can, I am using the previous figure, this figure, to derive the development length. You can see this one. So development length is nothing but how much length of the bar you should insert inside the concrete so that you will have a sufficient bond. Okay, so usually what is step 1? There are two types of bond, as I told you. That will be end anchorage bond. You can see the right side figure for the detail. End anchorage bond, and there is something called flexural bond. Flexural bond is the bond achieved for the steel bar because at the bending location, means maximum bending moment will occur at the center of the beam. So the max at that particular location, how much bond, that is a flexural bond. End anchorage bond is totally different. It is for the anchoring of the steel bar. Okay, you can see the right and correct and wrong figure I have shown on the left side. Okay, so how to derive the equation? Step 1, force is stress into area, sigma s into as. So for this derivation, step 1, step 2, step 3, please look at this figure. Okay, so force is nothing but stress into area, sigma s into as. So you know how much force I am applying, that much bond would have been developed. So equating both the forces, bond is nothing but tau BD, stress into area, tau BD into pi d into LD, circumference of the circle into the length of the bar, pi d into LD, equating both sides, cancelling the pi value, you will get, keeping LD one side, bring everything other side. So phi into sigma s divided by 4 tau BD. Okay, this is the formula for calculating the development length. Okay, so this tau BD will change, depends on based on your type of steel, whether you are using MS steel bar Fe 4 and 5 or whether the bar is under tension or compression, like I mentioned in the previous slide. Okay, so anchorage values, the third 1 mark possible here is, so you cannot use the directly the LD value what you are calculating from the previous slide, you cannot use that. If you are having a if you are inserting the steel bar beam reinforcement, if you are you obviously you will not keep straight, that what I mentioned in the previous slide. It is wrong to keep the steel bar straight. You will have some bending, whether you will bend 45 degree or you will bend 90 degree or you will bend 135. 135 is the angle to be bent for earthquake resistant structures. Okay, it is recommended minimum you should have 135 degree bending for the stirrups. Okay, so most of the case, if you are having hook, where 180 degree will be considered for a hook. Okay, so the anchorage factor is given as 4. What is anchorage factor? You can see the formula below. You just multiply that 4 times the diameter, 8 times the diameter, 12 times the diameter, 16 times the diameter, depends on the angle of bending. Okay, so to make sure, I am going to combine these 3 formulas. I have discussed what is bond stress and what are these factors, and I have discussed what is development length, this formula, and I have discussed what is this anchorage values. Okay, so using these 3, you should know this final formula. The question for this, from this chapter, they will ask related to development length required. Okay, development length required should be equal to development length standard, that is based on this formula, so minus AIF into phi. AIF is nothing but this anchorage factor. Okay, to make sure to understand all these 3 formulas, I will show some examples from 2 slides. Okay, so I will give some more 1 marks. Next thing is called splicing of bars. At the first session, I have discussed that in the market, the length of the steel bar available will be 6 meter or 12 meter, but you consider your beam is around 25 meter, 30 meter beam. Okay, very long beam. So you cannot have such a steel bar. Then you have to do the splicing, as shown in the figure right side. There you should have a splicing. How much lap to be provided? That splicing is nothing but a connection. How much bars you have lapped? Okay, that lap depends on whether your bar is under direct tension. Direct tension means somebody is pulling the steel bar out. Okay, the force acting is applying a direct tension. If in that case, the lap should not be lesser than 2 LD. LD is nothing but the LD calculated from the previous slide. This LD. Okay, so if your bar is under direct tension, you should use minimum 2 LD or 30 times the diameter of the bar. If bar is under bending tension is nothing but your beam. In a beam, tension will be acting at the bottom. So the steel bars below the neutral axis will be experiencing a bending tension. In that case, your lap length should not be lesser than LD or 30 times the diameter of the bar. Okay, for direct tension, they are giving a more lap length. If the bar is under direct compression or bending compression, direct compression, I hope you understood in the columns. In column, the bar will be under direct compression. In bending compression means the reinforcement provided above the neutral axis. In that case, the lap length should not be lesser than again LD or should not be lesser than 24 times the diameter of the bar. Okay, you should memorize these numbers. And if the diameter of the bar is more than 36 mm diameter, actually you cannot do. Consider 2-3 bundled bars, 2-3 36 mm diameter bars are to be spliced. It will be a very big circle. You won't get the actual splicing. Then consider 36 into 30 will be like 1 meter, 2 meter lapping will come. That is uneconomical. So most of the case, whenever you are having a diameter of more than 36, you will do the welding for splicing. You won't use the tie bars. Okay. So this is another for information. One more information about the anchorage length for shear reinforcement. As I told you earlier, if you are having for shear reinforcement, if you are having a 90-degree bending, then at least the development length should be 8 times the diameter. If you are having a 135-degree bending, at least you should have a length of 6 times the diameter. And if you are having a 180-degree bending, 180-degree bending of the shear reinforcement, at least you should have a 4 times the diameter of the bar. Okay. So I have discussed some 1 marks anywhere possible for objective questions. Okay, you can use somewhere. So I will discuss some 2 problems to make sure you understood the bond stress, you understood development length, and you understood the anchorage values. Okay. The question is, a plain MS bar, mild steel bar, they have given a bar diameter as phi itself is embedded in a M20 concrete with tau BD 1.2 MPa. So they are asking what is the minimum length of embedment if the bar is, I will come one by one, if the bar is straight in tension. Okay, so the bar is straight means there is no anchorage at all. The bar is straight in tension. Okay, so you know the formula LD is phi into sigma s by 4 tau BD. They have given sigma s for real. Most of the case we will use sigma s for every case, right? Obviously because of limit state method, 0.87 Fy, 0.87. This is mild steel bar. You will use 250, so you will get sigma s value 217.5 MPa. Okay, so first case they have given direct tension. So the tension and the actual tension, MS bar in tension, the factor is 1. So you will use the tau BD value directly. So I have used the tau BD value directly as 1.2. So the formula is 5 into 217.5 divided by 4 into 1.2. It is coming around 45 times the diameter of the bar is the answer. So the development length you should provide is 45 times the diameter of the bar. If your diameter of the bar is 10 mm, it is 450 mm you should provide as a lap. You should provide as a development length. Okay, so that's your first question answer. Second question, if the bar is under same tension, still it is under tension with a hook. Okay, hook means hook is nothing but 180-degree bend. Okay, so the LD required will be equal to, you know the formula, standard development length what you will provide minus anchorage factor into phi. Standard development length what you have provided for the same condition is 45 times the diameter of the bar minus AF into phi. What is AF? Anchorage factor for hook is 16. You can go back and see the table. It is 16. Subtract. You will, if you are providing a hook, your answer is 29 times the diameter of the bar. I hope it is clear. If you are keeping it straight, then you should provide 45 times the diameter of bar to get the sufficient bond. If you are providing as a hook means you are bending at 180 degree, then you no need to provide that much length of the bar. Okay, so you have to provide only 29 times the diameter of the bar. Okay, so third question, if your bar is under compression with 90-degree bend, if your bar is under compression at 90-degree bend, compression means compression for mild steel bar, it is 1.25 into tau BD. I hope you can go back to see the table. So compression in mild steel bar is 1.25 into tau BD. So you can see the formula below. I have multiplied 4 into 1.25 into 1.2. So you will get LD standard is 36.25, and they have mentioned you are having a 90-degree bend. If you are having a 90-degree bend, it is 8 times the diameter of the bar. So LD standard is 36 minus 8 times the diameter of the bar will give you 28 times the diameter of the bar is your answer. Okay, so I will give you a final question. HOSD bar is embedded in a M30 concrete. Now the bar is changing, nothing else, the same problem. Now it is HOSD bars. It is embedded in a M30 concrete with tau BD 1.5 MPa. So they are asking development length if there are two conditions. First question is Fe415 grade with 135 degree bend in tension. So they have given tension and Fe415 bar. Tension in Fe415 bar you will multiply. So HOST bar in tension, so 1.67 tau BD 2.4 MPa. Okay, so same formula, LD equal to 5 into sigma s by 4 tau BD. Sigma s, you know, 0.87 into 415 and 4 into tau BD I have calculated 2.4. I multiply, I will get a LD standard is 37.6 diameter of the bar. But LD required, they have mentioned 135 degree bend, right? So I have to minus 12 times the diameter bar from the answer, minus 12 times the diameter bar, I will get answer 25 times the diameter of the bar. That's it, very simple. So second question, Fe500 grade with 45 degree bend in compression. So Fe500 is nothing but HOST bars again in compression. So the tau BD I have to multiply by 2 tau BD. Okay, so 2 tau BD is nothing but 3 MPa. So I will get LD is equal to 5 into 0.87 into 500 divided by 4 into 2 tau BD is 3 MPa. So I will get 36 times the diameter of the bar, and I have to separate, it is a 45 degree bend, I have to separate only 4 times the diameter of the bar from that. So 36 minus 4 times the diameter of the bar is 32.25 times the diameter of the bar. Okay, so I hope maybe this was little quick, this bond and development length. You can pause and note, it's very simple. The three tables, if you know the three tables I have shown in the previous slides, it will be very simple to solve any type of problems from the bond and development length. Okay, so this completes the design of beam so far. Now I hope I made you to design a cross section for the beam. I made you to calculate how to calculate AST, how to calculate ASC, how to calculate shear reinforcement, how to calculate the development length, how to calculate the anchorage value. So now we know, as a overall we have completed the limit state design of a beam. Okay, whatever type of beam they will give, I hope you know to you are able to calculate everything for the beam. Okay, so there is something left in limit state of serviceability. We will do some deflection check for the beam, but mostly that will not change the overall design. So with this we are closing the beam topic. Okay, so if you have any doubt, any concern, if you have more details about some topic, you can mail me. Okay, so we'll discuss further sessions in next topics. Okay, thank you.